Okay, we will continue from our lesson on Monday, finishing up that 12.1. We talk about a little bit about a circle, right? So let me change direction a little bit to something you will see in section 6, 12.6, but we can talk about that right now. For example, let the equation of a sphere be 4x squared plus 4y squared plus 4c squared minus 8y plus 16z equals to 1. Now we know this is a circle because the ratio of x squared, y squared, and c squared are all the same. Just like the way we saw in algebra 2, like when we learn equation of a circle, right? That's, we have 4y squared, right? Okay, or 4x squared plus 4y squared, or maybe negative 2x squared minus 2y squared, like that, right? Basically, if they are on the same side and they have the same coefficient, then it will give us most likely a circle, even though it's not always though. Like I have to talk about the possibility of not having a circle because like this, we know this is a circle with radius 2, center at origin. Okay, but if I change that 4 becomes negative 4, then we know there's no such coordinate, right? Okay, but in general, if it satisfies certain condition, then it will give us equation of a circle. Now, the one we have here will give us equation of a sphere. Now, then, if this is a sphere, equation of a sphere, how do we find the center and then the radius? Let's see. To find the center and the radius, we will need to perform what we call completing square, right? But let's divide by 4 first so that the coefficient of x squared, y squared, and c squared are both all ones, positive ones. So if I divide by 4, divide by 4, divide by 4. Okay, and then from here, I complete the square. Let me group them first. So this is the x squared group, y squared minus 2y, and then c squared plus 4z, that's equals to 1/4. If I complete the square, what number I need to add here to complete it? Anybody? I wonder if you remember. Nobody say anything. Okay, you add 1. Okay, you add 1, and then for the c squared plus 4c, what should I add to complete the square? We will add 2, and I'm sorry, 2 squared, 4. Okay, now in case you wonder, oh, why do we do that, Thomas? Go back to your algebra 1. Okay, at this point, I don't even need to tell you anymore. Okay, yeah, you're supposed to know that already. Give me a second. I'm a bit picky on this. I want the equal sign to be lined up. Now then, I have x squared plus y minus 1 squared plus c plus 2 squared equals to 5 and 1/4, which is 21/4, huh? Okay, so from there we see, oh, this is the circle. I'm sorry, a sphere with center at 0, 1, -2. Okay, 0, 1, -2, coming from x minus 0, y minus 1, and z minus -2. Okay, and then on the radius is the square root of 21 over 2. Okay, we can answer some more questions. For example, how far, for example, maybe I go with another follow-up question. So that's for part A. Part B, what is the distance from the center to origin? How far is the center to the origin? Well, the center to origin, basically we use distance formula, d squared equals, let's call this d. So d squared equals to, the center is 0 minus origin, the x of the origin. See, this is 0, 1, -2, and the origin is 0, 0, 0, right? So we apply distance formula in 3 dimensions. That will give us 0 squared is 0, 1 squared is 1, -2 squared is 4. So this is 5. Therefore, the distance from the center of the circle to origin is square root of 5. Okay, then maybe we can ask some interesting question. For example, is origin inside the sphere or outside? That's an interesting question, right? But think about this. Imagine this is your sphere, right? The radius is square root of 21 over 2. Okay, whose square is 21 over 4. Now, the distance from origin to the center of the circle is square root of 5, whose square is 5. Now, we basically compare this 21 over 4 and 5. Which one is greater? You see, the distance from the center to the sphere, the radius of the sphere, is slightly more than, the square is slightly more than 5. This is 5.25, right? In decimal, this is 5.25. Is that right? Okay, so from there we see that see the radius of the circle is greater than the distance from the center to the origin. So consequently, the origin is inside in the interior of the sphere. Okay, now another thing we can do, we can ask, for example, I think I like this question more. Okay, what is the distance between the center of the circle to z-axis? How do you approach this? Now, sometimes before you answer a question, try to imagine first. Okay, so if I have a 3-dimensional coordinate c, let's say the c is somewhere here, right? Okay, let's call that x, y, z. if I want to find the distance between this coordinate xyz to the z-axis, we are basically looking at the distance from that xyz to the z-axis this way. But then what is the coordinate here that we could try to compare that to? The coordinate there will be, well, it is on the z-axis, right? That coordinate is on the z-axis, and therefore the coordinate must be 0, 0, z. Okay? Therefore, the distance from C, the center of the circle, to z-axis is basically the Pythagorean application to the x and the y-axis. Okay, so let's call this d's. I don't like that notation dc, but call this d1 then. Call it this d1. So d1 squared equals to the coordinate of C, which is 0, 1, -2, with the coordinate on the z-axis closest to that center, which is 0, 0, -2. Okay, which you think about, if you think about it, you will see that 0 minus 0, that's the difference of the x's, and then 1 minus 0, that's the difference of the y's, and then -2 minus -2, that's the difference of the z's. Okay, which is 1. So the distance from the center of the circle to the z-axis is 1. How about the distance from the center of the circle, basically from a point, I just called it the center, from a point to, let's say, YC plane? If you picture this, YC plane is this guy here. This is x-axis, this is y-axis, this is z-axis. The YC plane is this plane here. Is this plane here. This one. Okay? So the distance from that any coordinate to YC plane will be, let's take a look. It will be basically the distance from this point to that YC plane, right? Okay, so what is this coordinate here? If this is x, y, z, can you tell what is the coordinate here? On the YC plane, don't forget what we learned 2 days ago. Every coordinate on YC plane will look like, I wonder if you remember, 0, y, z, right? So if we have coordinate c, x, y, z, and we want to find the distance from that coordinate c to YC plane, you will see it's basically looking at the difference of the 1/2 difference. The x and y must be the same, right? Okay, so that is equal to, in this case, let me write the equation. Okay, let me write the equation. Let's call this d2. So d2 will be from 0, 1, -2 to 0, 1, -2. Oh, that's the same coordinate, huh? Right? So this 0 minus 0 squared plus 1 minus 1 squared plus -2 minus -2 squared. That would be 0. In other words, yes, the center happens to be on YC plane. Well, because what? Well, the x component of the center is already 0. Okay? You can try this if we want to find the distance from the center of this circle to, let's say, xy plane. Let's do it. Part E, what is the distance of this center, the center of this circle to xy plane? This is 0, 1, -2. And all the coordinate on xy plane must be 0, y. I'm sorry, 0. No, it's not 0 for you. It will be x, comma, y, comma, 0, right? Okay, in this case, the x and y must be 0 and 1. So the distance, basically the difference between this guy and this guy, right? -2. Oh, but it is distance, so it cannot be negative. You can also use formula though, the difference of the axis. If we call this d3, the difference of the axis plus the difference of the y's plus -2 minus 0 squared, right? Then d3 squared will be 4, therefore d3 equals to 2. Okay. Now let's go on midpoint formula. Midpoint formula. In 2D, we learned this in, I think, in algebra 1, if not in algebra 2. Midpoint of coordinate x1, y1 and x2, y2 is given by the coordinate midpoint for the axis and midpoint for the y's. Which, if you think about it, is basically the extension from one dimension. In one dimension, basically just a number line, right? If you have x1 here and then x2 here, the midpoint is basically you add those two and then divide it by 2. Right? That's in 1D, one dimension, number line. So in 2D, you extend it into the y component, and believe it or not, in 3D, that will be similar idea. Midpoint of x1, y1, z1, and x2, y2, z2 is given by the midpoint of each component, x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. Okay, now I will go on. Let's recall what we have in algebra 1. The following almost no relation to what we learned before, but more into the play that implicitly said or expressed in algebra 1. Notice that in 2 dimension, the equation x equals to 2 represent all coordinates. That's all coordinates with x component equals to 2, regardless the y. So when we graph that x equals to 2, you will see it's basically you pick x equals to 2, any x equals to 2, and then you connect the dots, right? Okay. Another way to look at that is the following. We see that this is x equals to 2, missing y variable. Then what happened is the graph will be parallel to y-axis. And you notice that we can do the same thing with, for example, y equals to -3, right? Okay, notice the behavior that if you have x and y axis, then y equals to -3 is missing x variable. Therefore, the graph will be parallel to x-axis. Now, why do I mention this? Because then, if we extend this to 3 dimension, we will notice the same behavior in 3 dimension. In 3 dimension, okay? How do we graph, for example, x plus y equals to 2 in 3 dimension? In 3 dimension, the way we imagine that is the following. This is 3 dimension, so it's supposed to be with 3 variables, but because we are missing variable z variable, it means the graph will be parallel to z-axis. Now, what you do then, first, try to graph that in 2 dimension. Graph that in 2 dimension first. So if I try to graph that in 2 dimension, it will look like this, approximately, right? This is 2, this is 2 for x and y in 2 dimension. Now, imagine that if we extend that to 3 dimension, then our z-axis will be here coming to us, right? Okay. So imagine you copy this line, x plus y equals to 2, you copy this line parallel to the z-axis. Let's try. If this is my x-axis, y-axis, z-axis, then the line that we have there in 3 dimension will be, let's start with the floor. It will be on the floor, like this, right? Okay, with this is 2, and then this is 2. Now then, copy this parallel to the z-axis. So what I will do is I will take this, I copy that. I wonder if I can copy that. Such that this point here will go up here. Like that. Okay, so we end up with this. Can you imagine that? What it looks like, by the way. It looks like a plane, and it's actually not bounded by these two lines only. It actually goes indefinitely far up and down. Okay, it's not only bounded by these two lines like the one I shaded, but it actually goes all the way up and down. But I only sketched part of that plane for us to be able to visualize that. Now, can you see that this plane here is actually parallel to z-axis? Okay, so part of 12.6 that we learn is called cylinder. In geometry, or I think I should say that in our Calc 3, is defined as a surface that is parallel to a line. Okay, especially for introduction, parallel to one of the axes. Okay, the one we have here, it's parallel to the z-axis. Now, to train our intuition, which is very important for this course, can you imagine what is the graph of y squared plus c squared equals to 4 look like? In 3 dimensions, of course. And the way we see, oh, this is missing x. So what I will do is I sketch the graph in 2 dimensions first, in this case the YC plane. This is actually a circle with radius 2. Okay, now you extend that, you copy paste that in 3 dimensions along x-axis because it's missing x-axis, right? So the way I do it, I will extend it in this way. I don't like this way of looking. Hold on. Borrow this. Now I get the line, axis. So let me use a thick black color. So this is the original circle on YC plane. Okay, and this is the extension in the positive x-axis, even though it also extends to the negative x-axis. Okay, and it looks like this. To help us identify that, let me do this way. Okay, and maybe you shade this part a bit to make it feel like it is a 3-dimensional, just the skin though. Okay, and then maybe another color somewhere else, just to get the feeling of that. Okay, the shadow, playing with the shadow, right? Okay, but again, it doesn't stop here. It doesn't stop at this circle here. No, it's actually extend further toward us and then extend further into the paper, okay, into the surface of our drawing. Okay. Now, with that said, then I think I can give you some suggested homework already. Now, again, suggested homework is for you to try, not to turn in. Let me write it here, suggested homework. From 12.1, I would like you to try number 2 to number 4, 7, 9 to 18, 20 to 22. And you don't need to do all of them. If you see that, you try a little bit. Let's say you try number 9, right? And then you feel comfortable with that. Then jump maybe to number 10. I'm sorry, jump maybe to number 12, 11 or 13. The odd numbers, every odd numbers, right? Every other odd numbers. And then you check with the back of the book. Okay? Actually, I have more from here. 23 to 38. Something for you to think about. And then I think the following is on the hard side, but please think about it. These two here may be on the hard side. Maybe, I don't know. Also, please take a look on section 12.6. 12.6 is a lot more complicated than this, but 12.6 consists of two parts. The first one cylinder, and then the second one is the conic thingy. Okay, so I do the easy one first here. Okay. Now that's for this 12.1. Well, please interrupt me if you have any question. Okay, if nobody asks me question, I just keep on going. After all, honestly, the material for this course is quite heavy. Yeah, the material for this course is quite heavy. Give me a second. Okay, let's go on to 12.2. 12.2 on factors. Now, I told you last time to please please read this section 12.2, because a lot of them actually just, what's called that? Terminologies. Okay, definition. A factor is a representation of magnitude and its direction. So you can say magnitude, basically in physics we call that scalar, just a number. But then it has direction associated to that. Okay, now in our class, let's say we have a factor from point A to point B. Now, from point A, the starting point is called initial point. And then point B is called terminal point. Now, if you see a factor like this, then we will write that as A, B with a ray on the top. Now, that ray it tells us from where to where. Okay, so if you see this notation, ray AB means it is a factor with initial point A, terminal point B. Now, sometimes we also call this, we give it a name with lowercase v with ray. sometimes. Okay, now our textbook, however, write a factor with a bold letter. When we handwrite, I require you to use the notation I have here. With the factor notation. Okay, with the ray notation on the top. Okay, unless you want to type it, then I don't mind you type your work with a bold, but trust me, if you type it, it will take you a longer time, a much longer time, and it just doesn't make sense. You know, it just doesn't make sense. Put it this way, whoever tried to type my math is basically somebody who tried purposely type it and then later on use that argument to say that Thomas, your quiz or your test is too long, but that's because that person has purposely do what I told them not to do and then complain for what they are doing. Okay. Do you think it's kind of strange? Okay, because we handwrite. By the way, this is actually this is a convention, not only in my class but in all classes though. In physics, when they write factor, they may use this notation instead of array or for factor notation. They use a cap or a hat, right? But we don't do that here. Okay, we don't do that here. We don't do that here. But Thomas, that's how I learned it in physics. Too bad you're in math class, and unfortunately, physics using math, not math using physics. Okay, we apply our math there. Once you go to that direction, then you use your teacher's notation, right? But in my class, use mine. I hate to say this, but in the past, I have some students from high school try to argue with me about that, you know, just to find out that, strangely, that student's teacher was my student. No need. In my class, we follow certain notation because that's what we do in math class, right? So if you go to higher level factor analysis, for example, we will still use this notation. Okay, the older textbook, they use this notation. Okay, now some notes. First one, factor V is equal to factor W. Two factors are equal to each other if and only if they have the same length and the same direction. Okay. I want to emphasize what people may misunderstand. Same length, same direction, they may have different initial and terminal points. Okay, so for example, if I have this factor here, right? From origin to here, this factor is the same to this factor. It's not about where they come from, where they go to, but it's about the movement. Okay, they have the same length and the same direction. I'm sure these two factors are exactly the same because I copy paste that, right? Even though they have different initial points and different terminal points, but the movements is the one counts. Okay, how far they go, how long they are, and the direction. Okay, in higher level, we say that factors, the idea of factors is coordinate free. Yeah, factors is coordinate free. Regardless where you start, regardless where you end, as long as you have the same length and the same direction, then those two factors are the same. Okay, next. The length of a factor, the length or norm or magnitude of factor V is denoted double absolute line with factor V inside in writing. In typing, maybe I type it here. If we type it, we can use just absolute notation, but the phi is being bold. Okay, see the difference though, see the difference. Now the thing is, in the past, I think the first time I taught this class in 2007, I think, I follow textbook notation and students get confused. What do they confuse with? Because the way they write like absolute of V like this. They are not, they then think, oh, this is just a number. I mean, it is a number, but the way they think is that the guy inside is just a variable or scalar. Okay, but what happened if it is a factor? Then it's not. To distinguish them, then I decided in the middle, I think after 2 weeks of the class, I say, you know what, let's just change the way we write it. When it comes to factor, we will use the factor notation on the top. And if it is magnitude, we use double absolute line. Okay. By the way, this double absolute line is still being used if you go to linear algebra and a much higher level. Okay. Give you some idea. I've been teaching this for a very long time, for how many years? Maybe since 2007, right? Okay. But recently, I think in the last 5 years, especially, we have a very great development in artificial intelligence. And the foundation, one of the big foundation of artificial intelligence is linear algebra. Besides statistic, of course, besides statistic, linear algebra, probability, and so on and so forth, right? But the foundation of linear algebra is basically factors. Okay? Now, if you are going to computer science, for example, and you really want to be relevant when you graduate, you better know that. Okay? Please don't tell me, Thomas, that's not what I'm going to do. Yeah, if you keep on using that argument not to do it right, you may end up doing nothing. Yeah, of course, at the end you will say, oh, that's not what I'm doing because I'm doing nothing anyway. I'm unemployed. Right? No, don't close the door for you yourself. Don't tell yourself that, no, I'm not going to do that. Instead, hey, you know what? I don't know if I'm going to use that or not. Why don't I just learn it now? Okay? That's for the norm, which we also call magnitude. In our class, we'll just call that length and magnitude. But in higher level, especially linear analysis, linear algebra, after linear algebra, you do linear analysis, you will end up calling that norm. Now, next, vector with initial point origin is called position vector. Next, the sum of vector v and vector w is the resultant of, I'm sorry, resultant with t here, displacement phi and then continued by w. So suppose, for example, this is vector v plus vector w that is equal to vector v. I copy paste this. And then be continued with vector w. Okay, now the resultant is this vector. This is phi plus w. Okay, and from here you also see that phi plus w equals to factors phi plus w is equal to factors w plus v. Now let's do some experiment. The nice thing about doing it on computer, I can do copy paste, right? So if I have vector v here plus vector w plus vector v, that is equal to vector w first and then continued by vector v. Okay, now let's show that they are actually exactly the same. How? I will match it here. Do you see that? Do you see that? Right? Okay. So the summation of factors is commutative. V plus W equals to W plus V. Okay. Now, next, scalar multiple of, give me a second. Number 5, note number 5, scalar multiple of vector v, let's call that kc, kv is vector v being stretched or shrunk by factor of k. In other words, the length is multiplied by k, but the direction is the same. Okay, so for example, our vector v earlier. Okay, so what does vector 2v means? 2v means you basically pancake that two vectors back to back like this. This is vector 2v. And it is algebraically correct, like vector v plus vector v equals to 2v. Okay, so you notice that the direction is still the same. Okay, the length is twice. Okay, so what is the length of 1/2 of v? If this is vector v, then the length of 1/2 of v will be exactly half of that, but still the same direction. Okay, half the length. 1/2 vector v is half the length of vector v, but the same direction. Now we go on to what happens if we have negative v. How do we represent negative v? Negative v is the same factor, but you reverse the direction. Okay, you reverse the direction. You see how I did it? Right? I copy paste, but I reverse the direction. So this is negative v. Okay. In this case, you basically multiply the length by a factor of -1 so that you reverse the direction. It is still parallel though. So negative v, factor negative v, is still parallel to factor v. Okay, but in my class, I will write it with this notation in details. In my class only. I learned this from my own teacher. So factor v, even though they are parallel, it is in opposite direction with factor negative v. You see that? Okay, this is parallel but opposite direction. Now factor v is parallel and the same direction with kv when k is positive. Okay, it will be parallel and opposite direction if the k is negative. Maybe I write down here. Vector v is parallel but in opposite direction with kv when the k is negative, the scalar is negative. Now, once we understand that negative factor is basically the same factor, but you reverse the direction, then we can introduce ourselves to subtraction. Factor v minus factor w is the same to factor v plus the opposite of factor w. Okay, so let's say this is our factor v, and this is my factor w. Okay, so v minus w is equal to factor v plus factor negative w. So I take this guy here, copy paste that, reverse. Actually, I don't like this. Reverse. Which means I have factor v no, that's not what I want. I have factor v and then continued with factor negative w. Okay, so the resulting factor is this. So this is factor v, this is factor negative w, and this is v minus w. Okay. Now, actually, my physics teacher actually then say this. You can just use factor w right away. Okay, you can just use factor w right away instead of flipping that first. Okay, but instead of using the continue from the initial point, you continue from the terminal point. Now, take a look what I meant. Okay, so what my physics teacher say this, to picture that, you start with this, right? And then you take this guy here, but you do the terminal points meet like that. You see what I mean? Okay, now then this factor here, you know what, let me copy this, the one we have here, copy, and to show that it match, right? To show that it match. It doesn't. Why it doesn't? Something not right. Supposed to. You know what, let me experiment. If I put them here, one of my thing is actually not correct. Hold on, give me a second. I start questioning my stuff here. Is this parallel? No, it's not, huh? You see, it's not parallel. That's not the correct way to do that. Let me erase that. Let me copy this again. Copy, paste, but then I want to reflect. Is there any way for me to reflect? Rotate. Yeah, flip. Horizontal or vertical, it's okay. And then flip again. This must be correct. That's the one I'm supposed to use here. Let me erase this. So my factor from here to yeah, let me just continue here. It's supposed to be one line though. From here to here. Okay, so let me grab that guy, copy that, paste here. Now, see, it matched, right? So we can express the subtraction of two factors also pictorially like this. Okay. Next, components of factors. A new topic, component of a factor. We will define the following. I, factor I, will be the unit x direction. Factor j is unit y direction. And factor k will be unit z direction. Factor. So from here, we will start putting numbers on our factors. If you notice that what we have learned before, so far, we don't really have numbers on the factors, right? We only say, oh, this is what factors and what factors are doing. Now we will start putting numbers. Okay, now suppose, for example, in two dimension, suppose I have a factor from here to here. Then this is a position factor, right? This is a position factor. And let's say this is the terminal points here is coordinate 4, 3. You know what? Let me change that. I don't like that. I want to use a coordinate here is coordinate 4, 3. So this factor here, if we call this, let's say factor A, then factor A is denoted by factor notation, not using parentheses, but using that wedge, side wedge, 4, 3. Which we can also write as 4 times x direction factor I plus 3 times y direction j. Okay, so if then I have another factor, let's call that factor b with components 2, -3, that is 2i plus -3j minus 3. You know what? Let me not using 3 there. Let me use 5, -5 instead. -5j. Then not only we can visualize that graphically, we can start doing that algebraically, like factor A plus factor B, for example, factor A plus factor B is basically adding 4, 3 by 2, -5, which is 6, -2. Okay, or if you like, you can write it in IJ notation. Okay, now the magnitude of factor A denoted this way, you remember? okay, is basically Pythagorean application to it. 4 square root of 4 squared, 3 squared, kada boom, that's equals to 5. The magnitude of factor B is square root of 2 squared plus negative 5 squared. That is square root of 4 plus 25. That's square root of 29. Of course, at this level, do not make it decimal. Just leave it like that. If you can simplify, simplify. Like for example, if you have square root of 48, for example, that's 16 times 3, right? So that will be 4 square root of 3, and leave it like that. Do not make it into decimal. Just leave it like that. Okay, that's the reason some instructors says even though you're working on calculus 3 times, do not use calculator, which I think is quite not reasonable if we have some application problem. Okay, but when we are still in the theoretical computation, do not make it into decimal, because that may implies you already start doing some rounding. Okay, furthermore, what does this notation mean? Magnitude of a plus b, that's basically the magnitude of factor 6 negative 2, which we already computed earlier. That's square root of 6 squared plus negative 2 squared. That is square root of 36 plus 4, square root of 40, which is 2 square root of 10. Okay, now this idea extends again to 3 dimension. The thing is, in 3 dimension, it's harder to graph it, right? That's why we need algebra. Okay, that's why we need algebra. Suppose, for example, we have factor C 3, 4, 1. Then what is the magnitude of factor C? Well, that will be square root of 3 squared plus 4 squared plus 1 squared. That's square root of 26. Okay, what is 2c then? Well, 2c, you multiply that factor by 2. That's factor 6, 8, 2. Okay? Now, with this said, then, in our textbook, there are properties for factors, which I already copy-paste here. I don't know which page you can see this, but we have the first property that the summation of 2 factors is commutative. Okay, a plus b, factors a plus b equals to factors b plus a. Okay, number 2, property number 2, actually the factors also have that associative property. Now, associative property basically say the following: if you're adding 3 factors, you can and actually that's the only way. The only way to add 3 factors is by adding 2 of them at once. Either the first 2 first, or you add the last 2 first. Okay, now associative property basically says the following: if you're adding 3 factors, okay, you have to do it 2 at a time. Okay, together with commutative property, when you add factors, you can do it in any order. Okay, ask yourself, since a very, very long time ago, when you learned how to add 3 numbers, right? Nobody, however smart that person, can add 3 numbers all at once. The way they do it, right? Even though it's really, really fast, they may have a very supercomputer brain, but the way that supercomputer works, still doing it 2 at a time. Okay. Now, number 3, if you have a factor adding factor 0, so this factor 0 here, basically this factor 0 here is basically factor 0, 0 or 0, 0, 0 in 3 dimension. Okay. And you see factor 0 is the identity factors on addition, and negative of a factor is the inverse addition of a factor. Okay, now and then number 5 and number 6, I forgot what you call this. Distribution property. Okay, the factor distribution and the scalar product, scalar distribution. Okay, number 7 and number 8, basically if you have scalar multiple of a multiple of a factor, that's basically the same to you multiply the scalars first and multiply by that factor 8. Okay, basically, in other words, by the way, what I meant by the other words here is actually an important idea. The important idea is basically, if you want to compute the length of factors, right? For example, you may need this later on. Suppose you have e cube 3 and then e cube -4. Let's say you have this factor here. Let's say you have this factor. And we want to compute the length. I'm sorry, I don't like that notation. I don't like this notation, very confusing. Let's say we want to compute the length of this. Now notice that it has common factor e cubed, right? You can factor that out first. And you end up computing the length of factor 3, 4, but you know that's 5, right? By Pythagorean theorem. Okay, instead of you do it long way. Some people like to do it long though. Some people just like it long, I understand, but you're working too hard for nothing. Okay, you will use this skill especially when we get to chapter 13, I think. Yeah, we will deal with this a lot. Okay, but what I'm saying is like this idea that the thing that we learned earlier, right? The same length, I mean the same direction with you stretch that by factor and multiply the length by k. Okay, that the idea of this one sentence is the one we apply here. Okay. Now let's go on. Unit factor, very important idea. Unit factor of factor v is denoted factor u with subscript factor v. Is a factor of length 1 parallel to v. Okay, so factor u, unit factor of factor v, for sure is parallel to factor v. Okay, in fact, parallel and the same direction. And the magnitude of factor, that unit factor, is equal to 1. How do we do that? How do we do this? We do it this way. Okay, unit factor or factor v will be, you take that factor v and then you divide it by its own length. For example, suppose we have the phi is equal to -3 and then 12 and then -4. Okay, then what is the magnitude of vector v? That will be the square root of -3 squared plus 12 squared plus -4 squared, which is square root of 9 plus 144 plus 16, which is square root of, I think it's 169, huh? Which is 13. So the unit factor for factor phi is basically that factor v divided by its own length, which we usually write as a fraction. Okay, and you can try to compute the magnitude of this unit factor. You will find that the length is actually 1. Okay. Suggested homework from here. Suggested homework from here is number 3, number 4, number 9 to 28, 29, 31, 32, 35, 36, 38. And if you have a chance, please think about this number 43 and number 47. You will see when I do give you the suggested homework, the one I circle is the one that may make you think a little bit, but it's more into the conceptual idea though. Let me box that here. Okay. Right now it's basically 5:50. Let's take a break, and then when we come back, we continue with we continue a little bit, maybe later. Yeah, maybe later, with some application problem from this section here. Okay, let's take a break. We come back at 6 p.m. Okay, let's continue. One little application of this factor into physics, for example, the use of factors in physics. This is a question, an example from our textbook. I think I don't misrecall it. This is example number 7 in our textbook. How do we use this? Now, what happened then? We have a mass being suspended by 2 ropes. Okay, the ropes happen to form angles 50 degrees and 52 degrees. Now, the question is then, what is the tension for each of them? Okay, what is the tension for T1 and T2? Okay, the factor and of course the magnitude. Okay, now what you don't want to happen, you use a rope that cannot sustain the tension, right? And therefore it will break, right? Okay, or on the other hand, if you can suspend this 100 pounds or 100 kilograms of mass in the air like this, using this in this situation, then we know the rope you have here and the rope you have here have the capacity to sustain that kind of tension. Okay, so let's try working on this. Let's first denote the magnitude of tension 1 by, let's call that A. Maybe I call that X. Yeah. No. Don't use X then. Let's call that A, and then the magnitude of tension 2 is B. Now, if these were our coordinate, then T1 has angle 50 degrees from negative x-axis, right? So factor T1 must be the magnitude A multiplied by the cosine of 130 degrees. Well, I use 130 degrees because I need to see it this way. Okay, the x component has to be negative, right? The x component has to be negative. And the y component will be a sine 130 degrees. The second tension, it will be B. If this is 32 degrees, this is 32 degrees, right? Okay, so that will be B cosine 32 degrees and B sine 32 degrees. Okay, now notice that if this mass is being suspended and stable, it means the following. It means the x component of T2 cancels the x component of T1. Okay, basically I'm saying that from the x point of view, from x component, A cosine 130 degrees minus B cosine 32 degrees is equal to 0. While when it comes to the y component, notice that the y component of T1 and the y component of T2 put together, both of them suspend at 100. Okay, the y component of T1 together with, I'm sorry, it should be plus here. It should be plus. The y component of T1 and the y component of T2 working together equals to 100. Now, we need to find A and B first. Okay, we just need to solve for A and B. Once we know what A, what B is, then you will know the exact expression for tension 1 and tension 2. Okay, I'm sorry, I write something wrong here. It should be sine. Then how do we solve this? How do we solve this? Notice that we basically now have a system of two equations, right? With two variables, A and B. Okay, from equation number 1, the x component, I can say that, let me solve for B. Can I? Yeah, let me solve for B. B is equal to negative A cosine 130 degrees over cosine 32 degrees. And then I substitute that into equation 2. So A sine 130 degrees minus A cosine 130 degrees over cosine 32 degrees times sine 32 degrees. That's equals to 100. Okay, however, these two guys put together give us what? That gives us tangent, right? Now I will factor the a out. Cosine 130 degrees, tangent 32 degrees, that's equals to 100. So factor A is equals to 100 divided by that ugly guy, sine 130 degrees minus cosine 130 degrees, tangent 32 degrees. Now then from here we use our calculator. Where's my calculator? I'm sorry, TI. Okay, so let's see, let me see my mode. It's already in degrees. Okay, so I'm ready. 100 divided by parenthesis sine 130 degrees close parenthesis minus cosine 130 degrees times tangent 32 degrees. That gives us the A. So A is equal to, what is that again? 85.63824. 85.63824. Yeah, suppose this 100 here is in kilograms. Oh, I'm not supposed to erase that. I need those. Yeah, suppose this guy here is in kilograms. Then the A here is also in kilograms. Okay, now once you find A, you can find B, right? Once you find A, you can find B. And just for example, then once we get that A, we are ready to find what is our tension 1. Tension 1 is 85.63824 cosine 130 degrees, 85.63824 sine 130 degrees. As you can see, cosine 130 degrees is negative. That will give us negative value. For the x component, for the y component, sine is positive. Sine in second quadrant is positive. It will give us positive y component. So as we expect, the T2 is in second quadrant. So the x component is negative. The y component is positive. Okay. And yeah, you just go on with your T2. So you using that A solve for B, right? You take it from here. Take it from here. You also already know your A, right? Okay. Now once you get your B, then you use that to find T2. Okay. That's for this 12.2. We use factors a lot in physics though. Okay. By the way, This is actually not the only way to do this problem. The way I showed you the work here, actually to show you how we use this to find, to use the components of T1 and T2. Okay, but somebody can do it this way also. If I use the diagram earlier, this is T1 and this is T2, for example. And then the weight is here, right? Now, so notice that T1 plus T2 supposed to counter the W. In other words, factor T1 plus factor T2 is plus factor W supposed to be 0. Okay, so if you just want to find the magnitude of T2 and the magnitude of T1, if you just want the magnitude, which we call A here, I'm sorry, that's not the correct notation. If we call magnitude of T1 is A, and magnitude of T2 is B, right? Notice that this is also T1. Then what you can do is to find the angle here. Let me use another color. You can use find the angle here, which I believe if this is 32, then this must be 58 degrees, right? Okay, and if this is what is that? 50 degrees, as I remember. If that's 50 degrees, then what will this be? This is 50 degrees and this is 32 degrees. That's 82 degrees. Right? Now we can find this guy here, which is the counter of W. We know that's actually 100, right? This is actually 100. Okay, using that this law of cosine, you can do that, or even law of sine. For example, A over 58 sine 58 degrees equals to 100 over sine 82 degrees. So A is equals to 100 sine 58 degrees over sine 82 degrees. So let's try 100 sine 58 degrees divided by sine 82 degrees. You see, exactly the same number, right? Okay, but the way I do it here, the second way of me doing that, did not break it up into the components. Okay, which is not the purpose of that example. Now, the purpose of this example is to make use of how we decompose the factor into x and y components and how these x and y components actually work together. Okay, but if you use the second method here, you still need to break it down though, because the final answer, the final question is not only the magnitude of the tensions, but also the tension itself is what factors. Okay. Next, let's go on to the next part. You will see the more we get into this course, then the more things we can do later on. Section 12.3 on dot product. Also called scalar product. In linear algebra, linear analysis, we call that inner product. even though the phrase inner product may mean something else. Okay, but every inner product, one of them dot product, will have certain properties. Okay, let's define a dot product. Definition: let vector v be phi1, phi2, phi3, and vector w be w1, w2, w3. Now I'd work on 3 dimension right away. You can just see that in 2 dimension. Then phi dot w is a scalar phi1 w1 plus phi2 w2 plus phi3 w3. And it is a scalar, or just a number, not a factor. Now, when you do the dot product, you have to put the dot here, and that dot is in the middle. So it's not decimal point. It's also not composition. You know, like in the past, in Algebra 2, we learned composition of function, right? Okay. No, not this circle here. Not a small empty circle. No, not this one. Not this one. Okay. It's a dot. It's a dot. It's a dot. And to make sure that you see your own dot, you make it a bit thicker. Okay, for example, if we have factor 2, 4, -3, dot, -1, 5, -2, we basically add the product of corresponding components. Okay, which is equals to 24. And try to do it mentally fast. Okay, the way I do it here. So instead of, I know some people like to do it long. Again, they will write it 2 times -1 plus 4 times 5 plus -3 times -2. That's not wrong, of course. That's not wrong. It's just like I think that's something students in Calculus 3 should be able to do mentally. Okay, this part here, try to do mentally. Okay. Next, properties of dot product. I have it somewhere here. Let me carry that up. Properties of dot product is given here. Okay, basically in number 2, you will see that dot product is commutative, and dot product has that distributive property. Okay, and number 4, dot product with scalar has associative property. Okay, now the one that I want to emphasize a bit is from number 1. Factor A dot factor A is basically if factor A is A1, A2, A3, then it will be A1, A1 plus A2, A2 plus A3, A3, which is A1 squared plus A2 squared plus A3 squared. Okay, but that is the square of the square root. That's the square of the magnitude of A. Okay, now that is an important property. We will use that here and there in proving. If you are in linear algebra later on, which I think you will take if you are going to engineering, you will take linear algebra, then you will use that property quite often. Now, next, physicist definition. Physicist or engineer's definition of dot product is the following. Now you will see that these two definitions are actually equivalent. In other words, from one, you can get the other one. So the dot product of A and B is the magnitude of vector A times the magnitude of vector B times the cosine of the included angle. Okay, so imagine if you have vector A and then vector B, and this is the included angle. Then the dot product is basically the product of the magnitudes multiplied by the cosine of that theta. Okay, you can see the proof. You can see the proof. See the proof of this definition. So they call this definition in physics, but it is actually derived from our definition. For the reason of time, I will not go over that, but you will see it is we use law of cosine in proving it. Law of cosines, and also the property number one we had earlier, vector A dot vector A equals to the magnitude of vector A squared. Yeah, those are the ingredients of the proof. Okay, now what we are interested in is this one here, important. Memorize this formula. Okay, because from there, then we come up with the following. Cosine theta, cosine of the included angle, is equal to the dot product of two factors divided by the product of their magnitudes. Okay, so for example, if I copy paste the example we have earlier, factor, let's call factor A equals to 2, 4, -3. Factor B is -1, 5, -2. We have computed earlier A dot B equals to -2 plus 20 plus 6, which is 24. Also, the magnitude of A is square root of 2 squared plus 4 squared plus -3 squared. That's square root of 29. Magnitude of B is square root of -1 squared plus 5 squared plus -2 squared. What's that? 25 plus 5, that's square root of 30. Okay, then cosine theta, the included angle. So let's say this is vector A, this is vector B. The theta here, right? Cosine theta equals to the dot product 24 divided by the product of the magnitudes. Now, then the angle theta must be the cosine inverse of that. From there, then you use your calculator. But please, when you use your calculator in your last step, okay, round it to 5 decimal places. Okay, in my class, if you do so to 5 decimal places. Which actually, to be more precise, later on you will see if we get very small number like 0.000 something, I prefer to call that 5 significant digits. Okay. So to find the angle between two factors, we use this formula. Okay. Now from here also we learn something important. So I think let me change the color. Notes, important one. Notes. Notice that cosine theta equals to 0 if and only if theta is pi over 2 or 3 pi over 2. Which basically means those two factors have angle A, and angle B forms 90 degrees. They are perpendicular. Okay. But at the same time, you see that cosine theta equals to 0. A number equals to 0, a fraction equals to 0 if the numerator equals to 0. Right? Okay. That's if A dot B equals to 0. So to check if two factors are perpendicular, what you do is you do the dot product, see if it's equal to 0. Okay, next, another topic in how we use this formula. Another one is in case of directional angles. Direction angles. Now the phrase direction angles refers to alpha, beta, gamma as follows. Now suppose we have that three-dimensional coordinate system. Of course, they are perpendicular to each other, right? And you have a factor sticking out. Let me make it a bit thicker. We have a factor sticking out like this. Thomas, I cannot really tell where is that factor actually pointing at. Is it pointing to behind YC plane or in front of YC plane? It's not clear. Now to make it clear, then I do the dashes to help us shadow that. Let's say I put it like this. Okay. Is it okay? Can you see that better now if I do that kind of reference dashes? Right? Okay, now angle alpha refers to the angle from positive x-axis to that factor. This is angle alpha. So angle alpha is angle formed by factor V, a factor, and positive x-axis. While angle, let me use another color, this one here. Angle beta is the angle formed by, hold on. That's the angle formed by a factor and positive z-axis. Positive y-axis, I'm sorry. So angle beta is actually the angle formed by this. This is angle beta. If you are going to work at JPL, like anything with aerospace, like not just the like not just a regular plane. I'm talking about outer space, the one you go to other planet thingy, the satellite thingy. Then you better know this alpha, beta, gamma. Okay, it simplifies a lot of computation though, compared to if you try to do it another way. Okay, and then gamma, what color do I want to use? Let me see. Let me use this color then. I hope it's visible. Angle gamma here is the angle formed by a factor and positive z-axis. Okay, now we use this alpha, beta, gamma a lot. What I want to show you here is a technique to find this alpha, beta, gamma. I will just do one of them. Okay, but I hope using from how we derive the formula, you see the technique that we actually use a lot. Okay, for example, suppose I want to find angle alpha. Suppose I want to find angle alpha. What you can do is you find, you see that you have a factor and an axis, right? But what we just learned earlier is the angle between two factors. How do I use what we learned just now, the angle between two factors, to find the angles between a factor and a line, in this case an axis, an x-axis, the x-axis. So what you can do is you take, you know what, let me use this highlight instead. You find a factor parallel to x-axis. Okay, notice that this factor, the one I highlight here, this factor, call this factor, what is the factor parallel to positive x-axis? I think we did call that factor I, right? But it doesn't have to be I though. You can use 1, 0, 0, which is I. You can use 2, 0, 0. You can use 3, 0, 0. Okay. So if we describe that further, angle alpha is the angle between factor V and factor I, right? From what we learned earlier, so cosine alpha is equal to V dot I over magnitude of V times magnitude of I. Now, the nice thing why I choose factor I inside, because it's already unit length, right? Okay, while phi dot I, if you see factor V, which is phi 1, phi 2, phi 3, if you dot that with I, that will give you which one? I want you to think about this. What is phi dot I? If you multiply that with factor I, so this factor I here is not I as imaginary number, but 100. No. Phi factor phi dot factor I will give you phi 1. Basically, the x component of that factor divided by the magnitude of phi times the magnitude of I, which is 1. Okay? Notice that cosine, if I go on further, cosine beta will be phi dot j using the same idea, right? I represent positive y-axis by unit factor j. And use the formula we have above. That will give us phi 2 over magnitude of factor v. Likewise, cosine gamma, that's factor v times unit factor k over the magnitude of factor v times the magnitude of factor k, which is phi 3 over factor v. Strangely, if you put these three things together, as a factor notation, cosine alpha, cosine beta, cosine gamma, that will give us a factor phi 1 over magnitude of phi, phi 2 over magnitude of phi, phi 3 over magnitude of v. I can factor that magnitude of phi out, and on the top we'll get phi 1, phi 2, phi 3, which is basically factor v. But factor phi divided by its own length is the unit factor of factor v. Okay, so suppose, for example, let's say we have factor a, which is 3, negative 4, and then 5, like that. Okay, we want to find alpha, beta, gamma. Find alpha, beta, and gamma, the direction angles. The way we do it, if you want to do it all at once, you find the magnitude first. Which is square root of 50, I believe. 5 square root of 2. So the unit factor of factor A is 3 over 5 radical 2, negative 4 over 5 radical 2, and 5 over 5 radical 2. Now, these unit factors represent cosine of factors of cosine alpha, cosine beta, and cosine gamma. Okay, fast forward. Then gamma equals to cosine inverse of 5 over 5 radical 2, which is cosine inverse of 1 over radical 2, which I do expect you at this point memorize that as pi over 4, 45 degrees. Okay, now this alpha beta, especially gamma, this alpha beta, especially gamma, is very important when you are designing an airplane, and it is being used, I believe, a lot when you design the fighter jet. Okay, because gamma is basically the gamma is basically imagine if you have a plane, right? If you have a fighter jet. Okay, now the angle gamma will tell us the angle of your direction to the vertical line. Okay, now so if your angle gamma greater than 90 degrees, what happens is your plane is facing down. Okay, your plane is facing down. And if your gamma is greater than 90 degrees, it's actually harder to pull it up. Okay, now it's not my field, at least, to talk about that, but at least I give you some idea on how we will use that alpha, beta, gamma, especially the gamma. Okay, that also give us something a lot of people don't realize that, though. In fact, I didn't realize that until my teacher, my professor, make that comment. Kind of strange, huh, Thomas? You took this class how many years ago? I took this class like around 26 years ago. But I still remember stuff that my professor said there, because my professor make a comment that I didn't expect. What comment? Note that cosine squared alpha plus cosine squared beta plus cosine squared gamma equals to 1. Why? Well, that's the length of unit circle squared. I mean, unit vector squared, right? Okay, that's the unit circle of vector A being squared. That gives you this look here. Okay, that gives you that look. Something nice to know. Something nice to know. How useful is this? Basically, in our navigation later on, okay, once you know alpha and beta, you know gamma. If you know gamma, then you know alpha and beta. If you know two angles, you know the third one. Okay, let's go on. I think this will be the last part of the section 2.3. I have approximately 20 minutes. Oh, it's doable. Okay, the thing is, like in this class, however, we don't do enough exercise. So I need you to do that, to please do your exercise. And please do me a favor. If you study, okay, try to do the suggested homework that I asked you to do. And then if you have any questions, send me an email. What I plan to do is on Saturday, right? On Saturday, my office hour, I don't expect any student show up or any student I have any question. If anybody have questions, I don't think they will stay for a long time. I answer and then they leave, right? That's what usually happen during my office hour. So what I plan to do is I will answer your questions and create a video, a supplemental video from your questions. Now, if you don't give me any questions, then I will pick some problems from our textbook and work it out this Saturday. Now, I'm not saying that you need to come. I'm saying that if you have things that you want me to answer in form of a video, then you tell me from the textbook what section, what problem, which question, and then I will try to explain that and create a video for those questions on Saturday, and then I make it supplemental video for you. Okay. Now, component and projection will be seen as follow. Suppose I have factor A. Suppose I have factor A. Follow me in writing, in graphing, because this may be a bit complicated. And then I have factor B. Now, projection of factor B onto A is the length of that, quote unquote, the length of that blue highlight. Okay, so let me mark it this way. Let me mark it that way. Then component of factor B onto A is defined to be, quote unquote, the length. I use quote unquote here because the length, as we know, supposed to be a positive number, but the length here may be negative. That's the length of that factor which we will call component of factor B onto factor A. Now, this highlight factor, the factor that I highlight, is called projection of factor B onto factor A. Now, imagine if you kind of like take the shadow of this factor B on the surface of A. Okay? Now, as you can see, this component of B, component of factor B onto factor A, is basically the length of factor B multiplied by cosine of the included angle. Think about it. Okay? Which is, if we derive a bit further, we know that cosine theta is equal to A dot B divided by magnitude of A times magnitude of B, which you will see that the magnitude of B, factor B cancels. So we get A dot B divided by magnitude of A. Which you can also say, that's the formula we use the most though. Okay, this is the formula we use the most. Component of factor B onto A. This is the formula we use the most. But we can also see that this guy here is the unit factor of A. Unit factor of A dot B. Now, the projection of B, the actual factor, the projection of factor B onto factor A is the actual factor. Okay, the actual factor, the one we highlight in blue. Now, that is parallel to factor A. Okay, think about that. Projection of B is parallel to onto A is parallel to A, factor A, and has the length of projection, the length of projection of B onto A is equal to quote-unquote the component of B onto A. Again, I use quote-unquote because when we say the length, it has to be positive, right? But component of B may be negative. Imagine if we have this situation, if this is A here and then this is B, then the component of B is actually the negative, okay? Because the angle is already more than 90 degrees, right? If the angle is more than 90 degrees, then the dot product is negative and therefore the component is negative. Okay, but if what I want to teach you is the following: if you know that two factors are parallel, okay, so they have the same direction, but they have different length, how do we find the factor, in this case, the projection of B onto A in terms of A and B? The way we do that is as follows. Projection of B onto A must be the scalar multiple of unit factor of A. Okay, this unit factor of A gives us the direction, Now the length is 1. Then how do we adjust the length? We get the length from here. This gives the length. Okay, so how do we find a factor if we know the direction parallel to another factor and we know the length of that? Okay, we will apply this idea later on. So component of B onto A, we have had that earlier. Component of B onto A is A dot B over magnitude of A, right? And then unit factor of A is A. By the way, this is not dot though. This is not dot. It's just scalar multiple. It's scalar multiple here. Okay, A over magnitude of A. Now, then we usually use this formula, A dot B over magnitude of A squared times factor A. So this is the formula we use. Okay. Examples. Suppose we have factor A equals to 2, -3, 4, and factor B is -3, 4, 1. The magnitude of A, I wonder if you can do it fast enough. Square root of 29, right? You find out how I do it. And then magnitude of factor B is square root of 26. Now then, how do we compute? To compute component and projection, we need to do the dot product first. So dot product will be -6, -12 plus 4, that's -14. So component of B onto A, factor B onto factor A, is the dot product over the magnitude of the screen, the receiving part. We use different color. This guy here is always the magnitude of the denominator. Okay? So it will be -14 over square root of 29. Now, because you see the component, it has negative value, then basically you are saying that, actually we even know that from A dot B, it means that theta is greater than 90 degrees. Okay, if A dot B is negative, that implies cosine of the included angle is negative, right? But cosine of the included angle is negative if the included angle is greater than 90 degrees. While the projection of B onto A will be A dot B over magnitude of A squared times factor A, which is -14, that's A dot B. Magnitude of A squared is square root of 29 squared, that's 29, multiplied by factor A, 2, -3, 4. Okay, which is -28 over 29, 42 over 29, and -56 over 29. Yeah, of course, component of A onto B is something you should try. Okay, no, they are not. They are usually not the same. Okay, component of factor A onto B will be A dot B, the dot product of those two, divided by the magnitude of the screen, in this case magnitude of B. Now projection of factor A onto factor B is A dot B over magnitude of B squared times factor B. Okay, not the same formula, but you can play around with that. Now, your suggested homework for this 12.3 will be, where's my note? I had my note earlier here. This is a lot though, but please do. Okay, from 2 to 30, 33 to 37, 39 to 48. I think 49, 51, 55, 61 is something good for you to see. Okay, and also number 53, number 62. Okay. Now you don't need to do all of them, but at least try, okay? Because what you don't want to happen is in your test later on, even though you can use cheat sheet, but you don't have time in your test to use your cheat sheet to find out what is dot product. Okay, I mean dot product we use that so often, so many times, such that if you still need to cheat from your cheat sheet for that, you don't have enough time for your test. Okay, yeah. Again, I said earlier, if you have any questions from these problems that I assign for you to try, you don't need to turn this in. Let me know if you want me to go over any one of them. Otherwise, this Saturday, I will do the recording for some problems from here. Okay, maybe some medium level one and slightly harder one, especially the one that I think is important for us. Okay, then that's for today. Any question?